My name is Joe Kuda. My project, the radio expansion tester. My sponsor is Poba Medical. Poba Medical is a balloon angioplasty company. They are based out of Flagstaff, Arizona. They design and manufacture medical balloons, shown in that picture on the right there. Angioplasty balloons are made with hollow tubes called extrusion. They're designed from thermoplastics. Thermoplastics are just a plastic material that has a very low melting point, so it's very easy to manipulate and shape. Some common materials that we use for our balloons are nylon, polyurethane, and PVAX. Here's just a bigger image of a balloon that we've blown. They're usually used in non-invasive procedures to block or to clear a blocked or narrowed artery. Usually if someone hears balloon angioplasty, they think of a stent. You would be correct. On that right image there, you see a metal stent wrapped around a balloon. Basically how the angioplasty procedure goes is here we have the catheter. The balloon is bonded over the top of it. There's a hole somewhere in the catheter there to help inflate the balloon. The metal stent is a braided metal material. It slips over there. So then when this catheter is inserted in an artery and maneuvered up through the body to the procedure point, the balloon will inflate. It'll push that metal stent out into the arterial walls and hold it in place, keeping it open. And then the balloon simply just deflates and is removed. So our project goal is to improve the inspection process for the extrusion that is used to make these balloons. Our original inspection process involves a visual inspection where we basically just look for any gel spots, fish eyes, any discrepancy in the material at all. Make sure that the product is okay before we move on. Diameter measurements are done by hand with the pin gauge testing over there. And then elongation testing is just stress and strain data being acquired. The material is fixed to this point down on the base of the compliance test fixture, and then also to the digital force gauge. Then it is just stretched up and the force is recorded to see how much it needs to stretch that material. Here's just a closer look of some nylon extrusion. As you can see, they're pretty small. That right image has the pin gauge inside there. Depending on the material and the size of extrusion, the wall thickness on the inside will vary, but nylon is usually the most commonly used. So for this device, the radial expansion tester, I decided to have about 4 sub-assemblies. The first one being an optical micrometer. The optical micrometer is just a device to take non-contact measurements of the diameter. This can be a camera or a laser, as long as it can read diameters between 0.02 of an inch to 2.5 inches. That's our constraints for this project. The air pressure system is just designed with a mandrel. The tubing of this extrusion will just fit over the mandrel like it does at pin gauge, and then we'll be able to inflate when needed. The compliance test fixture, we actually incorporated, so instead of having a separate device, it's all going to be on the same device. It'll be made with pneumatic clamps to pull the extrusion and keep any air from being released so it can inflate properly. And then lastly, we have a heating element. The heating element will help make the balloon just more, for the extrusion, more apt to stretch and inflate, as it will have to do that for the balloon process anyway. Some design decisions here. Here you can see the LS7070 key ints is what we went with. Cost wasn't really a factor put in here. We knew that we'd be spending a lot on a camera if we want the accuracy. So that wasn't really an issue here, but the LS7070 is a camera that will shoot a LED light beam here. That way, anything that intercepts with that beam will be captured and then displayed on the computer. So we can see a real-time image of that as well as a real-time measurement. This top right image also shows it without the rest of the components on that CAD model. The next design matrix I have is what kind of clamps to use for the test fixture. Pneumatic clamps, which are just air actuated cylinders. Airs, press a button, air is sucked out, and they clamp down and hold onto that material. That was chosen. It doesn't have the highest load capacity compared to the material handling clamps, but is more dependable when stretching and pulling to make sure there's no slips or snaps. You can see here on the air pressure system, or the full CAD model, how the air pressure system goes with the clamps. So here and here are our clamps. They are in guide rails, so then it will be able to stretch when needed. And this process is actually very similar to our BFM. The BFM is our balloon forming machine. This is what we actually use to form balloons. So this process, which is similar to the inspection of what we want the radial expansion tester to do, we have the clamps on each side, like shown in that CAD model. In the middle here, we have a heating element as well as a water jacket. The heating element contains a copper center mold in the shape of the balloon that we want. So, for example, if you can see, this is one of our balloons. The copper mold is just a hollow cylinder in that shape. When the extrusion is put through and inflated, it'll inflate and heat at the same time to create that shape. And then these tubes here for the water jacket will send water through and circulate it through around that copper mold, which will cool it down. And because it's a thermoplastic, it'll harden pretty quickly and hold its shape. On that right there is just a beefed up BFM. You can see the clamp and you can see the extrusion going into the heating element here. The last design decision I'll show you guys is the heating element. The main thing I was looking at was the copper tubing and the water bath heater. The water bath heater was my front runner for a while, but because of, well, after talking to the design team, we decided that it could get messy if there's any issues. Any internal and external pressures would have to change depending on what kind of material we use, as well as heating it, making sure it can heat consistently. So we decided to go with the copper tubing. Overall, this is a better choice just because it's so similar to our BFM heating element that if there is an issue, the engineers and the operators are familiar with that. So one last time, this CAD model, you can see the heating element here. It covers the mandrel where the extrusion would be placed. That'll heat up when the balloon or when the extrusion is inflated. This heating element can be moved out of the way, and in that bottom right image, you see the optical micrometer going down over it to get a measurement. Real quick, here's our budget. So like I said, this optical micrometer does take up most of the budget. That's okay, it was expected to. As for the heating element, we do have an R&D lab in the company's workshop. So some of these materials can be recycled from either old projects or just extra parts. I did add in some of the costs if we had to buy, like say we wanted a water jacket to regulate more of the shape of the extrusion when we're inflating it, or like if we need an extra force gauge, I did add that in. However, I think we can be under budget for sure by the end. I also did put aside about $1,500 for any extra supplies we might need. This is my Gantt chart for this semester. It mostly consisted of team development and design. And next semester, once I get to Arizona, I will be working on the 3D modeling and the guide rails, getting a prototype going, and then doing some product testing. Since I'll be doing this in my off time of work, I will have all the materials and facilities available to me, so I can do that on the weekends, and I hope to have it done pretty early in the semester. Here's just a calendar view. Thank you for listening. Are there any questions?